about congestion? Well, if your WAN, if your wide area network link is constantly, consistently congested, well, then you are going to want to upgrade that link. That's right. If you are consistently congested on that WAN link, then the solution is for you to get a better WAN link. But what if you're experiencing occasional, sporadic is a good word. What if you're experiencing sporadic congestion on a particular link? Well, this is when quality of services congestion management technology can definitely help out. So for that rare, for that sporadic kind of congestion, we want to go ahead and employ a approach of congestion management for QoS. By the way, congestion happens for a lot of different reasons in networks today, doesn't it? One of the ways that we know we're going to have congestion in the wide area network is due to speed mismatches, as I'll tell you in a moment. But, the approach of congestion management is called queuing. So when we see the term queuing, we know we're talking about congestion management. And what we're doing is we are doing something other than first in, first out. You see, an interface is made up of two different queue areas. There's what we call the hardware queue, otherwise known as HQ, or you'll often see it as TX ring or transmit ring. The hardware interface, a hardware queue on the interface, it's always first in, first out. So it is always operating in a manner where the first traffic into the hardware queue of the interface is the first traffic out. Where we can really get involved as network designers is in the software queue. The software queue, which is used to order packets before they hit the FIFO hardware queue, this is where we can do all kinds of different queuing strategies known generically as fancy queuing strategies. Again, we need this discipline because congestion is just a fact of life. Congestion might happen because of all of those high-speed LAN connections that are feeding into a slower WAN connection. So when we have this aggregate effect of the bandwidth hitting the slower speed interface, sure, we tend to get congestion. Remember, aggregation refers to being able to support the aggregate, the cumulative effect of all of those individuals wanting to use your network. Now, there are many, many different approaches that can be used to congestion management. There are many, as we like to say, queuing strategies. We already talked about first in, first out, right? First in, first out is what we have in the hardware queue, and it is not sophisticated at all, is it? It's just taking in packets that are first to arrive and putting those out. By the way, on a high-speed Cisco interface, this is the default throughout both queues, the software queue and the hardware queue. If it's a high-speed interface, that's the default for both queues. And remember, an approach to quality of service that you could take would be to dramatically over-provision your bandwidth so that you just do FIFO everywhere. On all of the hardware and software queues, it's just all FIFO. But this is unrealistic for most environments. In most environments, we're going to need some type of fancy queuing, like class-based weighted fair queuing. Excuse me, sneeze there. I don't know if you could hear it. Okay, so class-based weighted fair queuing or weighted fair queuing or low latency queuing. These are the most modern, sophisticated queuing strategies that will enable us to make sure that important packets are getting priority during times of congestion. We know that first in, first out doesn't do this type of prioritization. First in, first out queuing, when used in the software queue, yikes, it won't make a determination on if one packet is more important than the other. And do you remember how we can signal that one packet is more important than the other? Sure, a component of QoS that we mentioned is marking. So we mark traffic to indicate that one packet is more important than the other. So first in, first out, yikes, not sophisticated enough to prioritize some forms of traffic over other forms of traffic. As a matter of fact, if we were to just rely on FIFO and we were to experience congestion, we would have things like jitter, an increase in the overall consistent delay, and we might even get to the point where things that are very important to us, like our voice over IP traffic, we might get to the point where that is completely starved off of the network. One approach to fancy queuing that we can do in the software queue is weighted fair queuing. Weighted fair queuing is indeed a Cisco default on slow speed interfaces. What does Cisco consider slow speed? Well, these days, slow speed from Cisco is like 1 megabit per second or less. Roughly 1 megabit per second or less would be considered slow speed. That's a rough estimate. They may even be up to 2 megs now. But it's, let's say, I know for a fact it's between 1 and 2 megs would be considered slow speed. So Cisco will put weighted fair queuing in the software queue on these interfaces by default. The logic is, because the interface is slow speed, weighted fair queuing has got to be better than FIFO in that software queue. And Cisco is obviously correct here. That, yeah, on a slow speed interface, weighted fair queuing will be a lot better than FIFO. Because weighted fair queuing does is it sorts the traffic into flows. Okay? It will dynamically sort the traffic into flows, and then it will dedicate a queue inside the software queue for each flow, and it will try and allocate the bandwidth fairly. It will indeed look at the QoS markings, called IP precedence markings in this case. It will look at those IP precedence markings and give priority in this weighted fair queuing system to higher priority traffic. Weighted fair queuing is indeed not the best of solutions because we lack so much control over weighted fair queuing. It kind of just does its thing on its own. But it is far better than that FIFO approach. Why it's better is because little tiny interactive flows like voice over IP conversations, they get prioritized to the front of the software queue. This makes sure our high volume talkers don't totally monopolize the interface. Suddenly I'm reminded of the Seinfeld show here when we're talking high talkers and low talkers. But anyways, we definitely have a nice fairness to weighted fair queuing that makes sure that high priority, interactive, small little packet size conversations, like voice, don't get starved out by more high volume, monopolistic traffic flows. If you were to look at weighted fair queue using pretty colored pictures, you would of course see that hardware queue, which is FIFO only, and then you would see the weighted fair queuing system in the software queue. Notice that there is these different queues representing the different dynamically sorted flows, and they're hitting what's called a weighted fair queue scheduler, which will allow them to go from the software queue into the hardware queue. Notice, by the way, that if the queue does fill, well, then packets will start getting dropped, heaven forbid, but there will be a weighted fair queuing drop approach, so there will be some prioritization of who gets dropped. Hopefully, under this queuing system, we will have the dropping of lower priority packets. Now, the engineers of QoS looked at this and they said, yeah, okay, it's better than nothing. And by nothing, we of course mean first in, first out. But it definitely lacks the level of control that we would want, the level of control that we need, right? It doesn't allow us a lot of granular controls over what's going on. And they invented a congestion management technology as a result called custom queuing. Now, custom queuing is legacy, which means we no longer want to use it today. But you will still see it implemented out there in environments, so we need to be aware of it. Even though it's something we wouldn't set out to use, we may run across it in installations. Custom queuing is similar to weighted fair queuing, but instead you're going to define as the designer the 16 static queues. Up to 16 static queues can be defined. You then, as the designer, go ahead and assign a byte count for each queue. So in other words, you could say, all right, I want so many bytes to be sent from this queue, and then so many bytes to be sent from that queue, and then so many bytes to be sent from that queue. There is an important queue 0 that is reserved for the system. This is to make sure that you don't inadvertently starve out key messages that the routers themselves need to use to survive. Notice that you go in and you allocate either the amount of bytes for each of the custom queues, or you can literally say, all right, the number of packets for the custom queues that are going to be sent. Custom queuing was pretty good. Custom queuing was pretty darn good for a while. And that was the approach that would be used in the software queue in WAN environments for a while. But you know, when voice over IP came along, there was this little bit of a panic about custom queuing. Because custom queuing is not the greatest for voice. Why do we say custom queuing isn't the greatest for voice? Well, because of the round-robin nature of custom queuing. That is no way, shape, or form what we want for voice traffic. Think about it. It works in what's actually called a deficit round-robin fashion. But to simplify this discussion, let's just for now think of it as round-robin. What's going on here is you have these queues, right? I'll represent them as circles. Q1, Q2, Q3, Q4. And these queues you're configuring, let's say, with a number of packets to send. Okay, you can send 10 packets, you can send 20 packets, you can send 40 packets, you can send 100 packets over some time interval. Well, notice that, yeah, certainly queue number 4 is getting priority here, but notice that there's a round-robin approach. It's like, you know, okay, Q4 you go, then Q3 you get to go, then Q2 you get to go, then Q1 you get to go, and then it round-robins back to Q4. 3, 2, 1. This isn't good. Voice traffic needs what we call strict priority. It needs, another term for it is absolute priority. So this custom queuing, round robin servicing just is not appropriate for our voice over IP type of environment. And this is why they invented another legacy technology. It's now fallen out of fashion. It is now still considered legacy, but this is why they invented priority queuing. Priority queuing has us place packets into low, normal, medium, or high priority queue. And what happens here is when you take your voice and you place it in the high priority queue, it will indeed get strict, absolute priority. As a matter of fact, it can lead to a rather disastrous effect of queue starvation. Ew. Yikes. So priority queuing is no longer recommended and used today, at least in new designs, because the voice can go in the high priority queue, but if there is some malfunction and there's just way too much voice traffic going on, the other queues will not get serviced. I remember when my daughter was into silly bands, and we had to run all over town looking for these silly bands. Well, when we would find them at a store, which is analogous, by the way, to the high priority queue. So let's say this is the high priority queue here. When we would find them at a store that offered them at $2.99, as opposed to another store that might offer them at $5.99, we would absolutely be buying all of our silly bands from this store. We would only go to this store or to this store or to this store if the stores with the lower prices were out of these silly little things. Well, sure enough, we would never get to this store. We would never get to this store. If the $2.99 store ran out, we would go buy some for the $3.99. But the minute more came in at the $2.99 location, we would go right back there. Priority queuing, sure, it relates to silly band shopping, but I'll tell you, priority queuing no longer utilized because of this potential problem of queue starvation. So you might ask, well, what fancy queuing mechanism would we recommend for congestion management in a modern wide area network design? And if you do not have voice, if you are not doing voice over IP, well, then something you might want to consider if you're not doing voice over IP is called class-based weighted fair queuing. It's like weighted fair queuing, but on steroids. Please, please, no Roger Clemens jokes. Let's leave Roger Clemens alone. Weighted fair queuing, but on steroids. You get to go in and define those amounts of bandwidth that the various forms of traffic will get. Wow. You get to go in and guarantee at least minimum bandwidth reservations for different classes of traffic. So, with priority queuing, voice quality rocked, but we had queue starvation. Custom queuing, the round robin was too fair for voice. Weighted fair queuing, we don't control anything. It's just way too fair. Class-based weighted fair queuing becomes an ultimate solution if we're not running voice. We have the FIFO hardware queue, then we have this weighted fair queue scheduler, and we can go ahead and define exactly what forms of traffic go into these different queues. So you can see here I have a mission critical queue, a transactional traffic queue, an email queue, and then everything falls into a catch-all queue called class-default that you haven't defined classifications for. The weighted fair queue scheduler will now schedule this stuff, and you get to assign minimum bandwidth guarantees to all these forms of traffic. You can say, hey, mission critical traffic, you get at least 10 mega bandwidth. Transactional traffic, you get at least 2 mega bandwidth. Email, you get a half a mega bandwidth, and everything else is guaranteed at least a half a mega bandwidth. Amazingly powerful methodologies for controlling exactly how much bandwidth these various classifications are going to receive. Notice that inside a particular queue, by the way, notice, for instance, if we throw 3 different forms of traffic into the mission critical queue, notice inside an individual queue, it is FIFO. So you want to be careful. You don't want to throw too many forms of traffic inside one of the weighted fair queues because it's FIFO inside there, and now you may end up messing things up a bit. Okay, but what if we have voice? Class-based weighted fair queuing is the ultimate queuing solution for non-voice over IP environments. But what if we have voice over IP environments? Well, it's called low latency queuing. This adds a priority queue to the class-based weighted fair queuing system. So low latency queuing is often referred to as simply an extension of class-based weighted fair queuing. I'll say it again. Low latency queuing is nothing more than an extension of the class-based weighted fair queuing system. It adds a priority queue to the system in order to prioritize the voice traffic. But wait a minute. If we're adding a priority queue to this system, aren't we going to get into the queue starvation problem again? We don't want to starve any forms of traffic as a result of this strict or absolute prioritization for voice. How that is handled is the priority queue for voice is policed. Yeah, so we police the amount of bandwidth we guarantee for voice to make sure it can't exceed a particular bandwidth value. So inside the low latency queuing, queue starvation is avoided by policing that priority queue bandwidth. What a genius idea. So here's what low latency queuing would look like in pretty pictures. We notice that the voice gets its own priority treatment, and then the remaining traffic forms will be weighted fair queued thanks to our set bandwidth reservation amounts. Now, earlier on, we talked about how there was that sliding window concept, and how that sliding window concept with a congested interface could cause a really, really bad situation called TCP global synchronization. We are now going to talk about a new congestion mechanism. Specifically, we are going to talk about a new quality of service category. Let's review where we've been so far in this discussion of WAN QoS. Earlier on, we talked about shaping and policing, right? And then we just wrapped up a discussion of congestion management. Now we are going to talk about congestion avoidance, another category of differentiated services, QoS, that you will definitely see in the wide area network. Congestion avoidance, I shouldn't say definitely see, but I should say we will often see it in the wide area network. We remember with congestion avoidance that we're trying to guard against that whole global synchronization problem. You see, when we have what's called tail drop at the end of the queue, we've got our hardware queue, and then we've got our software queue. If the whole thing fills up, we'll start what's called tail dropping packets off of the end of the queue. Tail dropping packets could lead to voice over IP being completely starved out, and it could lead to that TCP global synchronization process. So the congestion avoidance mechanism that is often used is called random early detection, RED. And Cisco's implementation is called weighted RED. Weighted RED. Weighted random early detection. The job of this QoS tool is to try and prevent congestion from even occurring. It will randomly drop unimportant packets before the queue gets full. Wow. So we have packets sacrificing themselves for the good of the many. As the queue gets more and more full, by the way, more and more unimportant packets will be randomly dropped. So this is another tool, weighted RED, and this other QoS tool does congestion avoidance for us. The final category of quality of service tools at the WAN we want to cover is the category called link efficiency mechanisms. Okay, so the fourth and final category are called link efficiency mechanisms. Link efficiency mechanisms, there are two subcategories. They are compression and they are link fragmentation and interleaving. So we have compression and we have LFI that are subcategories of this link efficiency mechanisms. With compression, we're looking to take packets that can be compressed or portions of packets that can be compressed, and we're looking to squash it down. If you take what you're trying to send and make it smaller, you just increased the available bandwidth and you just decreased delay. There is TCP header compression. Take the header of the TCP packet and compress it. It actually compresses the IP and the TCP headers, and it reduces the header overhead from 40 bytes down to about 3 to 5 bytes. Great. There's also something called RTP header compression. This takes the IP, the UDP, and the RTP headers of a voice packet, and it squashes them down to about 2 to 4 bytes. We often find this approach used in voice over IP environments. And then finally, there's link fragmentation and interleaving. And there's 3 different flavors of link fragmentation and interleaving used today in networks. There's something called multi-link PPP with interleaving, and we would obviously use this in PPP environments. Then there's FRF.12 used with frame relay, and then there's FRF11 Annex C, and this technology is used with voice over frame relay. But you may be thinking, all right, Anthony, what is link fragmentation and interleaving? I mean, what exactly does that term mean? What does that quality of service mechanism really do? Well, let me show you what it really does. If you have a very slow speed WAN link, you can run into a problem even if you're doing congestion management like low latency queuing on it. If it's really slow, here's what can happen. We know we have the FIFO hardware queue, right? And then we know behind that there is the software queue, and we know we can do some fancy congestion management mechanisms in there. In the case of voice, we know we would be doing low latency queuing in there. Okay? So in the case of voice, we know that in the software queue, we're going to engage in low latency queuing. But here's what can happen. You can have a big packet called a jumbogram. You can have a big packet show up, and it's, let's say, an unimportant packet, but there's nothing else around. So the queuing system can say, go ahead, you get to go. And that big, giant jumbogram starts moving through the software queue and into the FIFO queue. And then, oh boy, you guessed it, a teeny weeny little, very important voice over IP packet arrives. Uh-oh. It gets stuck behind the jumbogram. The jumbogram is making its way through the software queue and the FIFO queue, and now the little teeny weeny voice over IP packet is stuck behind that jumbogram. So what does link fragmentation and interleaving do? It takes the jumbogram and it chops it up into fragments so that it can take the voice over IP packets and interleave them in between the fragments. How clever. So just think about the term link fragmentation and interleaving. It really does a great job of explaining what's going on here. We'll take those big jumbograms, we'll chop them up so that we can interleave voice packets in between them. And again, this would only be done on a real slow speed interface where we're having this particular problem. Well, let's wrap up Module 4's Lesson 4 by taking a look at some review questions. For example, we're concerned that your VoIP packets are experiencing too much jitter in your WAN environment, particularly due to a very slow link in the infrastructure. What can you do? Well, this is definitely where we might engage in that technology we just looked at of link fragmentation and interleaving. We also might try and use compression. Let's squash the packet headers down before we send them over this link. We may even have to increase the bandwidth. It gets so bad. So these are all valid solutions for this very slow link in the infrastructure that's struggling with voice. By the way, you would obviously also be doing congestion management on that link, right? So I guess it kind of goes without saying here that, yeah, we're also going to be engaging in low latency queuing on that slow link as well. What QoS technology will drop or remark packets that exceed a certain rate? Oh, great job out there to our live studio audience. We would traffic police. Yeah, so dropping or remarking packets, that is the job of traffic policing. Well, you have about reached the end of our 4th module here. Great job. We just got to wrap up our discussion of the enterprise edge by talking about some of the additional design criteria we need to use and talking about designing for things like remote access and virtual private networking, and talk about different enterprise branches that we might need to accommodate. So just some last minute odds and ends in the next lesson, and that will wrap up this important fourth module of the course, which focused on the enterprise edge.